Okay, last time we were defining sound intensity and sound intensity level, and now we're going to head off into a slightly different direction, and that will be the Doppler effect. You've encountered the Doppler effect numerous times in your life, I'm quite sure. Have you ever noticed, for instance, that if you're in a construction zone and there's somebody operating a jackhammer, when you drive toward the jackhammer, the pitch of the jackhammer seems to be a little bit higher. And then when you drive by, you notice the pitch drops to something a bit lower. That would be an example of the Doppler effect, and that would be for the case where you have a moving observer. So what's going on there is that let's say you're just standing here. We'll think about you moving in a bit. But first we'll just say you're standing here. So all these waves are heading at you at the speed of sound, which we'll say is v here. And let's say in some time t, make it a second, whatever, that ordinarily this many waves would just pass through your location. In time t. All right, now let's say that you, the observer, are walking towards our source of sound at some speed VO for speed of observer. Well, in some amount of time delta t, you would have ended up, say, over here. So in addition to the waves that you would have heard if you just plain stood still, you also walk through a couple bonus a few extra bonus wavefronts. I'll call these the extra waves. That you hear if you are walking towards the source. So in addition to the ones that you would have heard anyway if you're just standing still, the act of you walking towards the source means that you'll walk through a couple extra in the same amount of time. The math to get the resultant frequency that you hear is a bit tedious and not terribly instructive, so I'll just go ahead and quote the result. The frequency that the observer, so this is an O here, not a naught. I'm sorry, the frequency of the observer here, which is f, would be equal to the frequency of the source, which that is an f naught, times 1 plus or minus the velocity of the observer, VO, over v, the speed of sound. The plus sign is if the observer is approaching the source, and the minus sign is if the observer is receding from the source. As if you're heading the other way, you're basically running away from wavefronts, and so they wouldn't have hit your head yet. So just to make a concrete example out of this, let's say that somebody was striking a tuning fork at concert A, so that would be 440 hertz, and you were walking towards the source at, let's say, 20 meters per second. What frequency would you hear? Well, you would hear F equals, so just plugging into the equation here, you'd have 440 hertz times 1. And here we would be picking the plus sign because you are going towards the source. and you're going towards the source at 20 meters per second compared to the speed of sound at 343 meters per second. And this will yield 466 hertz. So noticeably higher, you know, a good couple of notes higher than if you were just standing still. Because you're not walking at 20 meters per second, but yeah, that's a reasonable speed to be in a car. Okay, now, so that's if the observer is moving. Now, what if the source is moving? You've probably encountered that too. If you've ever been to a car race, you've heard the car drive by the grandstands. You'll hear as the car approaches, the engine note is high, and as the car passes the grandstand, the pitch of the engine note drops. So let's go and take a look at what would be going on there. So here it's more useful to think about the actual wave fronts being emitted. So we will start by, so this is moving source. So let's start by, we'll just draw you in right here. And it'll be easier for me to note where the sources were going backwards. So let's say at the end of the scenario, the source was just emitting a wave here. Well, one period of oscillation earlier, it was here. One period earlier, it was there. One period earlier, it was there. So the source is moving toward you at speed v sub s for v source. So we'll say this is time 0, 1, 2, 3 periods of the sound. So at the time when this is being made, since the source is moving slower than the speed of sound, we will have emitted the wavefront from location 2 that was emitted when the source is at location 2 will be, will be past your current position at, sorry about that. Let's try that again. Got it. There. So it'll be centered on position 2. Sorry about that. There we go. It'll be centered on position 2, but it'll be past position 3 because the wave is moving faster than the source. Now let's go take a look at when it was emitted from position 1. That will be centered on position, I think I need my wave to be a little bigger. Yeah, I do. Try that again. There, something like that. So they'll be centered on position 1, and the one from position 0 is probably going to be going right through your eardrum at the moment. So let's try drawing that one. Oops, God help us all. There. Hey, stop it. There. So that's going to look something like that, and all these distances should be about the same, but my artwork sucks. Anyway, the upshot is that if the source is moving toward you, the wavelength that you hear will be shorter than the wavelength that was of the sound that was actually emitted. Oops, and there. And this is just because so this is the wavelength you hear. And this is just because the source is chasing after its own sound waves. Similarly, the wavelength that you hear over here, if you were, say, standing over on this side, you can see that this wavelength is a lot longer. So here you would hear a higher frequency because of the shorter wavelength. Here, because of the longer wavelength, you would hear a lower frequency. Again, I'll skip the tedious algebra and just quote the result. The frequency that you would hear would be the frequency of the source over 1 minus or plus the speed of the source over the speed of sound. And again, we would be picking the minus sign if the source is approaching, and the plus sign here now if the source is receding. So in both equations I gave you, the upper sign is for approach and the bottom sign is for receding. So again, just to make that concrete, we can do our same example here and say if it were 440 hertz, and the source were approaching you at 20 meters per second. See, with the minus sign here, that's going to ensure the denominator's number less than 1, and that will make sure that the frequency goes up. That's honestly how I remember, is I know if you're approaching it'll be higher, if you're receding it'll be lower, and then I think about which plus or minus sign will give me the sign that I want. So that's going to work out to be divide, there we go, 467 hertz. So a little different than the other example, but very comparable. As you approach the speed of sound, the differences will get more extreme. And so you might ask yourself, okay, well, what happens if the source does move faster than the speed of sound? After all, that is totally a thing. That is totally possible. And so the answer there is it's still the same kind of logic as what's happening here. So here we're going faster than the speed of sound. But now the thing is the source is outrunning its own wavefronts. So let's say this is the instant that we are currently making a wavefront. So then these are greater times in the past. Again, our sound waves will be centered around their corresponding points, and farther back in time will give us bigger wavefronts. There we go, something like that. And if I didn't totally boof up drawing this, what you'll get, whoops, stop it. There. What you'll get, and I didn't draw it very well at all, so that last wavefront should be bigger. What you'll get is that all the sound waves are piling up. So let's try to maybe make that a little clearer here. Something like that. Yeah, something like that. So the deal is that all the wavefronts pile up to make what we call a shock wave. And these shock waves carry an awful lot of energy. For instance, the crack of a whip is actually the end of the whip going faster than the speed of sound, and what you're hearing there is the shock wave. And of course, the more extreme example is a supersonic aircraft going faster than the speed of sound. Even if they're flying at a pretty decent altitude, that shock wave can be so severe it can destroy windows in buildings and stuff like that. This is also part of the reason why, for instance, rocket launch sites have typically about a 5-mile secure perimeter. One is for the obvious reason of what if the rocket blows up, but the other is so that you're far enough away that when the rocket goes supersonic, that the shock wave won't do terrible damage to your eardrums. Okay. In the next video, we'll take a look at standing waves and how we can have like an organ pipe make a sound. So catch you in the next one.